Swayam Prabha. Digital India. Educated India.
Well, we have so far seen the non-equilibrium cooling of steel in particular. We have this continuous cooling transformation diagrams, and what happens at different cooling rates has been already discussed. How the martensite start forms, how the martensite forms and finishes. Supposing martensite start temperature is above the room temperature, martensite finish is below the room temperature, what happens? All those issues have been discussed. Now, the location of these martensite start and martensite finish temperatures depends upon the chemical composition and the cooling rate. Now, if the chemical composition is such that the martensite finish is just below the room temperature, martensite start is above the room temperature, then you will have austenite and martensite combined together. On the other hand, if martensite start itself is a little below the room temperature over here, then martensite does not form until the room temperature has been surpassed and it is cooled below the room temperature. So, what it means is that materials like austenitic stainless steel, for example, which has got 18% chromium and 8% nickel, have a martensite start temperature much lower than the room temperature. So, at room temperature, even if you cool it fast, you cool at whatever rate you want, still it is not going to form martensite, it will still remain fully austenite. So, martensite start temperature is well below the room temperature. So, I mean, although this figure gives a indication that martensite start temperature is above the room temperature, that is not the case usually. It all depends on the chemical composition, degree of working, mechanical working, and the rate of cooling also. So that if you want to either suppress or take the martensite start up, one can do it in various ways. So, I told you one way is alloying elements. So, alloying elements are used to suppress the martensite start temperature below the room temperature. So, here austenite stabilizing elements, meaning you have carbon itself is an austenite stabilizing element. Then you have vanadium, aluminum, titanium, zirconium, nickel. So, these are all austenite stabilizers. So, these are these enhance the range in which austenite becomes stable. So, the martensitic range gets suppressed well below the room temperature. So, there are steels with high manganese. So, where chemical composition is such that you have the martensite start just below the room temperature. So, martensite start is just below the room temperature. So, now at room temperature, if you cold work the material is relatively soft, but then as you work the material, because of mechanical working, because of mechanical energy that is supplied to the material, the martensite start comes above the room temperature. So, mechanical working in a way shifts the martensite start above the room temperature. Again, the chemical composition also matters. So, it is not that any step to adjust martensite start and finish can be done in isolation. So, you need the right kind of chemical composition also to adjust these martensite start and finish temperatures. So, what happens is even if you continuously cool the material to room temperature and martensite start is just below the room temperature, there is no issue, there is no martensite that is formed. Only austenite phase will be formed, and that austenite phase will be relatively soft. Now this material, when it is worked, starts becoming hard very rapidly. Why? Because the martensite goes slightly above the room temperature and martensite begins to form. And as the martensite continuously begins to form with increasing mechanical working, the entire chunk of material gets transformed to martensite due to mechanical working. So the mechanical energy that is imparted does the job. So typically in let us say hammers, road roller equipment, road rollers use this kind of principle, where at the time of fixing the outer rim onto the road roller, the material is soft because it is done at a very high temperature. It is in austenitic phase, it cools to room temperature, it is still in austenitic phase. But then as it starts doing its job of road rolling, it undergoes very severe amount of strain, severe amount of working by the sheer weight of the road roller itself and the hardness of the surface it does rolling on. And so progressively it gets hardened. So with additional work, the road roller rim tends to get hardened. So this is what happens when you use the same kind of material for crushers and things like that, where wear resistance progressively grows with additional use. So initially the wear resistance is relatively small because the material is relatively soft, but then as the working takes place, as the strain energy is supplied to the material, the strain induced martensite gets formed. And this happens with many kinds of materials, where you do not want, let us say, failure of the material, you want the material to withstand very high amount of strain. There you would like strain induced martensite to form inside the material and then increase the uniform deformation of the material. So the strength goes up, the hardness goes up, and initially the material is soft, something that is desired by the manufacturer. So basically this is again one scheme whereby during working, during its service period, the mechanical properties continue to get enhanced. So you have chemical composition playing a role, the mechanical working also playing a role in deciding the martensite start and martensite finish. So it is not mandatory that martensite start should occur above the room temperature or at high temperatures. It could well be below the room temperature, it could be suppressed far below. For instance, if you take austenitic stainless steel, you have these cans being used for cryogenic liquids. For example, you want to do some what is called a cryogenic treatment, you can store this liquid nitrogen and such fluids in cans made from austenitic stainless steel. That is because the structure remains FCC, the face centered cubic structure is retained, it does not get transformed to martensite. So it does not become brittle, it retains its toughness as well as the fact that it does not it is not prone to DBTT, ductile brittle transition temperature. So we have seen how this austenite gets progressively transformed to different kinds of perlite, different fineness of perlite, and then how fine bainite, so another phase called bainite is formed depending upon at what temperature you desire the transformation. Another heat treatment we have seen is about the patenting of wires, particularly for hoists and ropes for heavy duty lifting purpose. So where perlite is the structure that is expected, again these properties or this structure cannot be achieved purely by heat treatment, it needs the chemical composition to be of that specific type, meaning the carbon percentage should be 0.8%, and exactly at 0.8% the eutectoid transformation takes place, and after that you have the entire thickness of the rope or entire thickness of the wire being in a pearlitic state. So, it has got very high strength. Even if it deforms plastically, the strain hardening is very high, the strain hardening rate is very high. So, supposing you were to overload this, if you were to overload this rope made of this pearlitic steel, then it will undergo plastic deformation. It will not break all of a sudden, it will undergo small amount of plastic deformation, it become harder, and therefore, it will still be able to support the weight of the lift or the weight of the load that you are lifting up. You have to be conscious of the fact that you have overloaded the material and overloaded the wires, you have overloaded the ropes, and you have to be careful next time you lift using this overloaded rope, because you have to understand that by overloading it you could well have gone beyond the yield point of the material, and then you might have resulted in some plastic deformation. So, if that has happened, it is better to not continue with it, because you do not want it to keep on elongating with progressive overloads. So, one can overload once in a while, but then and these wires are therefore little more forgiving, in the sense that occasional overload does not lead to the failure of the wire. It essentially undergoes small amount of plastic deformation and it will work harden, it work hardens very rapidly. So, basically this austenitic transformation to perlite, directly to perlite, 100% perlite, imparts good amount of strength to the wire. Then we saw a few other heat treatments where we wanted martensite, but then we did not want to lose the fracture toughness. So, we looked at the martempering as a possible means of of achieving that, and then we had a number of austempering and martempering type of heat treatments, where you get bainite in case of austempering. Mar forming is another thing which we saw, where instead of holding the material at a particular temperature, one could work the material, increasing the dislocation density, and therefore increasing the distribution. The martensite would nucleate at different locations and therefore gets uniformly spread. So, fine martensite would be generated as a result of this Mar forming. And then we saw about what kind of annealing is used. So, we have stress relief annealing as the first step in annealing. Annealing has got 3 different steps. One is stress relief, recrystallization and grain growth, of which if we want to relieve the residual stress, or if we want to do stress relief, then it is called as incomplete annealing. And so, that is the point, is that here the crystal structure does not change, the dislocation density also does not change, but the stresses which were present in the material, the elastic stresses get relieved, because we bring the yield point of the material below the level of the elastic stresses. So, there is local yielding taking place and the stresses get relieved, but the microstructure as such does not change, in the sense no new crystals would form, and no dislocation density is also not changed. Now, if you look at the annealing using different properties, so you have very high strength after mechanical working, okay, and then after annealing the strength comes down quite significantly, and therefore, the ductility tends to go up very significantly after annealing. So, this is what we have found. We have also seen how the grain growth takes place, or how grain size changes. You have an initial grain size of let us say which is coarse or fine. Then you have 2 stages of grain growth, one is non-uniform grain growth, and then there is a period of uniform grain growth. So, inherently coarse grains continue to remain coarse, they do not really grow further coarse, whereas finer grains have a reason to become coarse, because when you heat the material, beyond a certain time, the there is a tendency to minimize the surface energy of the grains. So, what happens is fine grains having a large grain boundary area has a much greater surface energy that is present, and in order to minimize that, you have grain growth to reduce the surface energy, and thereby coarse grains form. So, the fine grains have the highest propensity to coarsen, particularly when we subject the material to, let us say, ultra or to very high levels of plastic deformation, severe plastic deformation. You get ultra fine grain size, UFG, ultra fine grain size. So, you have another level of fineness of grains which is much below this level of fine grains, it is ultra fine grains. So, the rate of coarsening of ultra fine grains will be extremely high. So, very small amount of heat is good enough to start coarsening the grains, because there the surface energy is extremely high, and therefore, a small amount of heat is enough to get the grains to coarsen to minimize the surface energy. So, that is the point where now this is true for a constant temperature, and so we are seeing how time results in coarsening. So, beyond a certain exposure you have uniform grain growth, and for relatively smaller exposure you have non-uniform grain growth, which is preceded by an so called incubation period. So, we have also seen where the inherently fine and coarse grain steel is there. So, for instance, if it is an inherently fine grain steel, the grain growth up to a certain limit is a certain temperature relatively small, then it takes off very rapidly. Now, when you have ultra fine grain steels, then this point of rapid grain growth, of the initiation of rapid grain growth, moves to the left, meaning at much lower temperatures the grain growth will start, and this rapid grain growth will start. So, finer the grain size, the shift of this point, this transition from a relatively gentle increase in grain size to a very rapid increase in grain size. So, this transition will shift to the left, meaning to the lower and lower temperatures. So, that is the most important thing that is indicated here. Then we have seen during heat treatment what is the effect of heating rate. So, we need to take cognizance of the chemical composition. Again, heat treatment and chemical composition are intimately related, and so the final outcome of the heat treatment will depend upon what was the rate of heating, what was the rate of what was the time of holding at that temperature, what was the size of the part, and what was the cooling rate, and what was the cooling medium in which the cooling was performed. So, in this we found that for large workpieces you need to gradually heat the furnace, not heat it directly here as shown here, because if you directly heat it this way, then the temperature differential being very high, the heating rate initially itself rises too much, whereas here the heating rate gradually increases and then tapers off. Whereas in case of forced heating with low carbon steels, you heat heat the furnace to a very high levels of temperature, and increase the temperature differential between the workpiece and the furnace. So, then the heating rate initially becomes extremely high. So, we have seen the distinction between gas and oil fired furnace versus salt bath furnaces, where temperature control is much better than salt bath furnace, and therefore, the heating time and holding time are also much lesser in case of a salt bath furnace. Whereas, there are different kinds of salt bath and salt bath compositions, and there are certain features each one has, particularly the deleterious effects of these salts on decarburization of steel, particularly because steel has got carbon in it, and decarburization would lead to very non-uniform distribution of carbon over the entire steel mass. So, if the surface gets decarburized, for example, surface becomes soft and becomes prone to fatigue damage and surface deformation, surface becomes relatively weaker. So, we come to the point of oxidation and decarburization of steel, and this is basically the reaction of iron with oxygen water vapor and carbon dioxide decarbonization the reaction of carbon in steel with hydrogen and oxygen. That is because if you take if carbon is lost to say formation of CO2, then it is important, I mean then you will have less carbon on the surface and more carbon to the interior. So, carbon gradient gets established within this within the mass of the material. So, we use quenching media as air itself as in case of normalizing, but then water, oil, molten salts, aqueous solutions give different kinds of cooling rates. So, so as a result we use different quench media. If you see here, you have a temperature on the x axis and the cooling rate on the y axis. So, here you have temperatures rise starting with 800 and coming down to 0. You have the heating and then up to a certain temperature and then cooling very rapidly. So, if you take just the water as a quenching medium, so you see that if you quench, then the cooling rate, the cooling rate is the maximum cooling rate that is achievable is quite limited because it is just water. But then if you add 10% of sodium chloride, that is 10% of salt, then the cooling rate that is maximum cooling rate achievable becomes very high. So, by addition of 10% sodium chloride with the same water at the same temperature at 20 degrees centigrade, water at 20 degrees centigrade, which is assumed to be the room temperature, then you get a very high cooling rate, which is which can be good in one case, it can be bad at in other cases. For example, if it is a massive component or it is of high carbon steel, etc., then very high cooling rate can create problems. So, you need to therefore use the judgment as to whether you should add 10% NaCl or not. If you do not add 10% NaCl, then this kind of cooling rate would be obtained, which is much more desirable. If you put sodium hydroxide to the extent of 50%, then you get a cooling rate which is less than sodium chloride, but more than just water. So, any additions to water at 20 degrees centigrade, be it NaOH or be it NaCl, will result in a increase in cooling rate. And so, again one has to use one judgment about not only the cooling rate, but also the reactivity of that addition with the material you are trying to quench and harden. So, by addition of NaCl, so a sodium chloride is a salt of sodium ions and chlorine ions. Chlorine ions are highly reactive in nature. So, you can have corrosive effects if you leave it for a very long time in the salt water. Similarly, sodium hydroxide can attack the surface of steel in case it is left for prolonged durations, and comparatively very gentle cooling rates, particularly when you want to cool down at relatively low cooling rates. Again the same example of high carbon material being heated to a very high temperature, you would not like too high a cooling rate. Oil by virtue of its chemical composition, meaning oil will tend to decompose if it is subjected to very large amount of heat. So, you need to therefore take care that the temperature of oil does not rise too much, and and oil does not decompose. So, now if you quench in oil, then the temperature of oil has to be maintained at a relatively lower level, and the cooling rate which oil gives you are extremely modest. They are so about 200 degrees centigrade, 300 degrees centigrade per second are the kinds of cooling rates, orders of magnitude of cooling rates that oil can provide. So, we have a different kinds of quench media which can give you a cooling rate in the range from 2300 degrees centigrade per second to say 250 to 300 degrees centigrade per second when dipped in NaCl or in dipped in NaCl solution in water or in oil. So, this is actually brine, it is called as brine, and this is sodium hydroxide in water. So, this is how the difference in hardness is indicated. So, if you take the different diameter of shafts which have been quenched. So, on the y axis you have hardness, the medium of quenching is water or oil. So, you have a choice between water and oil. So, here you have the performance under water, here you have performance in oil. So, the carbon percentage is just 0.45% carbon. So, it is just a plain carbon steel. So, now when you have quenched it in water, so what happens is as the diameter continues to increase, the hardness distribution becomes shallower and shallower, because the outside and to inside. So, if you take the surface to the interior, you see that as the diameter tends to increase, with water cooling is very fast, and therefore, as the diameter tends to decrease, the hardness is much greater. So, the level of hardness. So, if you look at a relatively smaller diameter, then the overall hardness is much greater, whereas larger diameters would have overall hardness which is much lower, because the cooling rate which is seen by different regions is different. At the surface you see a very high cooling rate, at the interior the cooling rates are proportionally slower. If the diameter is small, the entire section sees the same cooling rate, and that is why the overall hardness is much greater. Well, even in a thin section, the central portion suffers from relatively smaller cooling rate, but then that cooling rate is much higher than what the center of this bigger diameter would see. So, the hardness variation, the qualitative variation is the same, because the central portion will cool the last, the surface will cool first, the rate of cooling seen by the surface will be maximum. But then if the center is very close to the surface, meaning the diameter is very less, then the cooling rates will be practically the same, and therefore, the hardness difference will not be very high, and the center will harden very rapidly. So, the hardness range will be the smallest. Here if you see the diameter is bigger. So, now you have a greater variation in hardness, the diameter is greater here. So, there is a hardness is maximum at the surface, minimum at the center, and the minimum at the center is far lower as compared to when the diameter is small. So, when you have a smaller diameter with water, you practically get through hardening of the material. That is, the hardness at the center, even at the center, is far higher with a thinner workpiece compared to a thicker workpiece or workpiece with a much greater diameter. Now, oil gives you a much gentle cooling rate. The oil gives you a much gentle cooling rate, due to which even if there is a small diameter to the tune of 25 millimeters, the hardness itself is achieved is much lower, because a lower cooling rate, and the distribution is also much more gentle. So, again here you can use oil for say tool steels or materials having very high alloying content with low thermal conductivity, where you do not want a very high rate of cooling. You do not want too much of differential hardness being created. So, you would like to have a gentle variation in the hardness. Surface has to be hard, and towards the interior you have a relatively gentle gradient of hardness right up to the center. So, that is something which can be achieved using oil. So, you have oil hardening non-shrinking, OHNS, as a very popular grade of tool steel which is used, and that is hardened in oil for a very homogeneous microstructure without any residual stresses induced during the cooling process. The extent of hardenability. Now, can any material be hardened? We have already seen that that is not the case. Again, the process of heat treatment or hardening is intimately connected with the chemical composition. So, if we see that cooling rate degrees centigrade per second at 700 degrees centigrade, you have a corresponding bar diameter which is shown. So, at the surface the cooling rate is very high. Towards the interior the cooling rate comes down to 2.4 degrees centigrade per second. So, at the surface it is very high, towards the it becomes smaller. Now, the corresponding bar diameter that will cool down is in still water. If you were to quench a bar diameter in still water, you will have so 25 will 50 75, so 100 mm diameter bar. This is what happens. So, it will have sorry, yeah. So, if you look at the distance from the quenched end of a Jomini bar in millimeters, then you have a hardness increase. So, if you were to quench with water, or if you were to quench with oil, or if you were to quench with something else, you will have different hardness distribution. As we saw in the previous slide, the cooling rate would be maximum with sodium chloride being mixed with water. So, if you were to do if you were to impinge brine onto this, then the cooling rate will be very rapid and the hardness will be extremely high, and so you will have a very high cooling rate. Even at the towards this side, the cooling rate that will be felt will be much higher. So, heat will be extracted much more rapidly, and so the diameter of the maximum diameter of the bar which could be quenched in brine will be that much higher. So, a higher cooling rate will therefore enhance the hardness of the material. Here you see a still oil quench. You see that there is still oil quench, and see here at the surface you have a very high cooling rate, and then as you come to the interior of the bar, so 100 mm, so the cooling rate is much lower, whereas with water quenching it is much higher. So, if you when you quench the in water, the same bar diameter of 100 millimeters has got 6.3 centigrade per second as the cooling rate, whereas the oil, which is much more gentler, it has got 100 mm as the I mean for 100 mm bar diameter, about 2.8 to 3 degrees centigrade per second as the cooling rate at the center. Now, different steels have different cooling rates, and therefore, the hardness from the quenched end of the Jomini bar would be would determine the hardenability of the material. So, if you look at the hardness versus distance, you will find that as we go away from this interface, the hardness would be high here up to a certain distance and then drop down to a relatively low level as we move away from here. So, now if we look at this kind of curve for different materials, you have just plain carbon steel of 0.4, 0.95 carbon steel. So, you have, as you see here, a very high value of hardness very close to the surface. So, at very large cooling rates, the martensite gets formed on the surface. The thermal conductivity of the material will change due to this phase transformation, and then as you go away from the quenched end of the Jomini bar, the hardness drops very significantly, because the rate of heat extraction also drops very significantly. So, if it is just 0.95% carbon or 0.4% carbon, if you are quenching it in let us say water, so then you will get only very small amount of surface hardening, but the hardness levels will be very high of course, because large carbon means more hardness, small carbon means relatively lesser amount of hardness. Now compare that with 1% chrome moly steel, or you have high molybdenum steel, manganese molybdenum, so here the hardness is obtained is quite significant. So, even if you go away from this interface right up to here, the hardness variation is much smaller in case of these highly alloyed materials as compared to the unalloyed materials. So, the hardenability of alloyed materials where you have added manganese, molybdenum, chromium molybdenum, 1.5% nickel chrome molybdenum. So, here practically the throughout the entire length of up to 50 millimeters, the hardness remains the same. So, if this Jomini bar has got a height of 100 millimeters, but then if you go to say halfway, still the hardness is practically the same. So, one can always, so what it means is that if you take a bar of 100 millimeter diameter, since it is the hardness remains constant over 50 millimeter section, if you take a bar of 100 diameter of nickel chrome molybdenum steel, you will be able to get uniform hardness over the 100 diameter bar. So, that is what it means over here. Now, if you look at the consequences of the cooling rate, you have what is called as deep hardening and shallow hardening as two consequences. So, shallow hardening results from a relatively lower percentage of carbon. So, you see that the carbon, so only surface hardening has taken place. So, it is a very shallow hardening that occurs, whereas deep hardening means the depth of hardening is much higher, and the extent of hardening, the magnitude of increase in hardness, the magnitude of hardness that you get is also extremely high. So, that is called as deep hardening or maybe through hardening taking place, as you see in case of 1.5% nickel chrome moly steel. Water and oil we have already seen as two different quenching media, which result in different degrees of cooling rates, and therefore different diameters of shafts that can be hardened. So, this shows the configuration of the of how the Jomini end quench test is conducted, and depending on whether it is oil or what kind of quenching medium it is, you will get different gradients of the of cooling, and therefore the diameter of the workpiece that can be through hardened will therefore be more with water as compared to oil. So, this is what happens when we quench it, let us say in water. You have different kinds of heat treatments, and if you take now a 3-dimensional object, large object being quenched, then you have conventional quenching with a single medium. Here what happens is, since the single medium has got a certain rate of heat removal, the surface cools much faster than the core, and so you have to take care that the core does not enter into this, so that you have the entire conversion, entire cross section being converted to martensite to the extent possible. Again, here what we see is that we have surface and core hardening, cooling at different rates, and then they are held for some time, and then they are cooled down. So, we have seen here that we have already seen this outstempering process, but then here we have got bainite with 20% of austenite, right. And then if you do a cryogenic treatment on this, like if you subject these to cryogenic treatment, then the retained austenite will get transformed to martensite again. So, you will be left with no retained austenite at all. Now, one advantage of retained austenite is that it will increase the toughness of the material. At the same time, it will also soften the steel. So, which means if you want very high hardness, retained austenite will become a spoil sport. So, if you want really high hardness, then you or maybe very high wear resistance, you would go for cryogenic treatment, get all austenite transformed to martensite, and that will give you a completely transformed material to martensite with all wear resistant properties and very high level of hardness. Now, if you take Mar tempering, there is less volume change due to large quantity of retained austenite. So, the advantage of retaining austenite is also that there is the volume change is relatively minimal. Possibility of self tempering of martensite is possible over here. That is less warping as transformation occurs in simultaneously. So, if you look at this, the transformation is occurring simultaneously. If the transformation occurs at different times, then there is a due to volume changes, there is possibility of warping or dimensional distortions, as it is called. Then there is a lesser risk of quench cracks appearing on the product, because now what is happening is you have equalized the temperature, you have a lot of austenite that is retained, part of it is transformed to martensite, but not everything, and then you have tempered martensite. So, as a result of that, you can get good amount of fracture toughness here. Now, here what is shown is that self tempering of martensite is shown over here. So, here what is happening is self tempering of martensite, which means that now the surface cools down the fast. So, at the fastest, so it forms the martensite fast. The core cools a little slower, and so it has got more retained austenite. Now, this heat at the center which is contained in the material, that itself will do the tempering of the martensite that has formed. So, that is what we mean by self tempering of martensite. So, the heat within the product itself, that heat is going to do the tempering operations. You don't need a separate tempering operation. Okay. And then one point that is to be noted is austenite has got low stability between 500 to 600 degrees centigrade, and therefore, one can easily harden thin articles of carbon steel and thicker ones of alloy steel, because thin articles of carbon steel would get through hardened and also get tempered. So, it will get very rapidly hardened because of austenite has got very low stability and propensity to get transformed to martensite. For thicker alloy steel structures also you can harden to martensite, and by virtue of the heat content inside, that martensite formed can be self tempered. Now, you see that see how this transformation occurs. So, here you have the old phase to new phase type of transformation. You have growth of this martensite taking place. So, if there is a lack of continuity and disorder at the interface, then the coherent growth is stopped. So, the martensitic transformation, as we know, is diffusionless transformation. There is no diffusion taking place because there is no time and temperature, which are the two driving forces, which are the two necessities for diffusion to take place. So, they are not available. You are cooling at a very rapid rate. As a result, the martensitic transformation uses coherency between austenite and martensite lattices. So, the atomic movements are very small. So, when the transformation takes place, it takes place without any diffusion. It takes place purely by atomic movements less than the interatomic distance and at a low interfacial energy barrier. So, as long as there is no plastic deformation taking place at the interface, there is no problem. You can have the coherency maintained, and therefore, the interface continues to remain coherent. However, if there is a disorder that is created by mechanical working, for example, or because of any other reason, let us say there are stresses being present, or due to which there is non-coherency being created. So, if there is non-coherency that is created, then the martensite interface tends to stop growing. The disorder or lack of continuity also stops the growth of martensite. So, martensitic transformation is a very important transformation which uses the coherency between the two lattices, austenite and martensite. So, this is the old phase essentially is austenite in this case, and new phase is the newly formed martensite. And wherever there is lack of coherency, the transformation is stopped. So, now here we see the effect of percentage of carbon on martensite start and martensite finish. So, as you increase the percentage of carbon, the martensite finish tends to get suppressed to much below the room temperature. So, to or even below 0. So, which means that at room temperature what you are going to have is martensite plus some retained austenite, and that is how cryogenic treatment becomes important. The typical domain of tool steel application is here, where the carbon percentages are very high, 1.2, 1.5, one can go up to 1.5 as well, and then you have about 120 minus 125 degrees centigrade or so as martensite finish temperature. So, you have some retained austenite which also does a world of good where impact is involved. Supposing the tool steel is going to be used under impact conditions, okay, let us say forging dies where there is an impact involved. So, particularly hammer forging for instance, then you need some austenite to be present so that it gets its toughness from austenite. And so, the retained austenite provides the kind of toughness without converting the entire structure into martensite. For cold working dies, let us say press working dies for example, or blanking dies. So, there you would like everything to become martensite. So, cryogenic treatment for especially for cutting dies or cutting tools would be in order, because you want essentially to carry out a separating process, meaning you want to separate out some material from the main chunk of material, for which addition of large percentage of carbon and then doing cryogenic treatment will result in a very high hardness, giving you a very high level of material property. Now, sometimes you need to have tempered martensite. For example, you have very high cooling rate, as in case of 10% sodium chloride, that is brine. Now, if you have lost the fracture toughness in the process, if the fracture toughness has gone below the level you expect, then it is very important to temper the martensites by tempering operation. Okay. So, this is so the martensite will decompose at temperatures below 350 degrees centigrade, okay, and form tempered martensite, and it is a supersaturated solution of carbon in alpha ion. Now, the reason why it is supersaturated solution is because there is no diffusion that is possible. There is no diffusion taking place while the formation of martensite got formed, and then this tempered martensite remains a supersaturated solution of carbon in alpha ion with inclusions of highly dispersed iron carbide crystals bonded coherently to the alpha solid solution lattice. So, basically this is what finally happens. So, what you do is that when you temper martensite, you basically have alpha ion and Fe3C which gives us strength with because you have iron carbide bonded coherently with the alpha solid solution lattice. So, that gives the strength, and the fact that you have alpha ion means that the toughness you had lost in martensite is now recovered, because now alpha ion is present. So, now it is more body centered cubic, and then you find that the excess carbon in alpha ion can react with iron to form iron carbide as well. So, if you see here, you have 1.2% carbon. Carbon content of martensite is very high for 1.2% carbon. The tempering temperature is very high. So, if the tempering temperature is relatively low for very high percentage of carbon, because the carbon is ready to come out. The solubility of carbon in alpha ion is very small. So, the carbon from body centered tetragonal martensite will come out at a much lower temperature as compared to when the carbon is inherently less. So, if you have set 1.2% carbon, and then you start tempering at even a lower temperature of 100 degrees centigrade, you can get much lower carbon that is left behind in the martensite, so that martensite becomes a little softer. The carbon coming out reacts with iron and then creates cementite, meaning Fe3C, iron carbide, and then that iron carbide is another hard phase. So, you have tempered the martensite, you have got back the lost fracture toughness, and then you also have gained in terms of formation of iron carbide and alpha ion, providing the relatively good amount of toughness. So, if you look at 0.6% carbon, the tempering temperatures are relatively higher. 0.4% carbon, it is further high, and that is because the carbon is readily not, carbon does not come out readily from this lattice, and so if you have small amount of carbon, you need a relatively lower a higher tempering temperature. For large amount of carbon, large percentages of carbon, you need relatively lower tempering temperature. And as the carbon goes out, as tempering proceeds, then you get toughness because of the formation of alpha ion. So, we have seen this salt baths as a quenching media, and different so these melt at different melting points, and so these are so what you do is that the cooling rate is adjusted by the temperature of melting of each of these baths. So, we have heated the material to a certain temperature, and then you have held the you have used a particular composition of the bath which governs the melting point of the molten bath material. So, you have for example 221 degrees centigrade as the melting temperature of melting point of this mixture, and then what it means is that you would after quenching this will get marginally heated. So, the salt bath will acquire the heat from the material being quenched, and but then this temperature can always be held at 221 degrees centigrade or 220 degrees centigrade roughly, so that you have a controlled cooling rate, a repeatably controlled cooling rate. So, cooling in molten salts is only by convection, and agitation enhances the cooling rate significantly. So, you have convection and agitation, both enhance the cooling rate very significantly, and heating may be conducted in molten chloride. So, if you have so here we have nitrates and hydroxide, but in the previous slides where we saw the salt bath composition, we found that the chlorides are capable of much higher temperature, and therefore it is important to heat in the presence of these chlorides. So, the salt bath of chloride is can be used for heating, and these nitrate salt baths can be used for cooling. We need to note that the salts can decompose at if the temperature is set too high. So, if the temperature of the bath rises due to repeated quenching, so many things are being quenched, so that the bath continues to rise in temperature, then it can also decompose. So, that care has to be taken. Plus there should be no moisture, so because these molten salts at high temperatures are highly averse to the presence of moisture. So, it can even cause explosion. Now, let us see the pros and cons of or relative cooling rates of different salts, salt combinations. So, different salt combinations give a much gentler cooling rate as compared to water. Water being equal to 1, you get 39% of that at sodium nitrate and potassium nitrate and sodium nitrate. So, this mixture gives you just 39% of the relative cooling rate. So, and at 400 degrees centigrade, potassium hydroxide sodium hydroxide mixture would give you a very small cooling rate. So, the cooling rates are dependent upon the nature of the bath and the temperature at which it is maintained. For example, at potassium hydroxide sodium hydroxide can be maintained between any temperature 200, 300, 350, 400, and the corresponding cooling rates are reduced. So, the sum total of effectiveness of different quench media is given here. So, as the carbon percentage increases, the hardness, particularly for the initial percentages of carbon, increases very rapidly. So, typically up to 0.8% it will increase very rapidly, and therefore, thereafter it will be taper off to a certain hardness range. So, you cannot harden indefinitely. So, you cannot harden to any amount of hardness. So, you can harden it to about 700 750 BHN depending on the percentage of carbon. So, if you have let us say 1% carbon, then your hardness can be increased by water quenching to 700. Whereas, if you do oil quenching, the maximum hardness you can get is close to 450 or so. So, 450 BHN would be that. If you do normalizing, the cooling rate and normalizing is much greater, is much gentler than that of oil as well as water, and so cooling in air is something that will give a much gentler smaller cooling rate and therefore a lower hardness. So, even if the carbon percentage is same, the cooling medium, namely air, will give you a lower hardness. Again, whether you should normalize, whether you should cool in water, or whether you should be quenching in oil will be determined by what are the kind of stresses that are going to be set up during quenching, what are the kind of phases that will be formed during the quenching process. Most importantly, the volume changes taking place, the stresses induced by these, and therefore, you need to consider the cross section, the thermal conductivity of the material being quenched, and the quenching medium, the rate of heat transfer that is taking place, the quenching medium temperature. So, all these parameters will govern the final rate of cooling and the stresses that will be set up during the course of cooling. So, then you have annealing, that is furnace cooling. So, if you have furnace cooling, even a gentler cooling rate can be provided, and similarly annealing at a certain temperature. So, you basically do not cool it, you maintain the temperature to a certain level and then cool it in the furnace towards the end. So, there are different possibilities. You have typical tempering temperatures, so different kinds of hardness being obtained, and then if the hardness is too much, you would like to temper it between 250 degrees centigrade and 400 degrees centigrade. No, you would not like to temper between these two temperatures because of tempering embrittlement. So, this is typical problem with steels, not with any non-ferrous materials. In steels, you get temper embrittlement within a certain temperature range. A high cooling rate in the martensitic range, heavier the cross section of the workpiece, coarser the austenite grains, larger will be the residual stress in hardening. So, we need to have fine grain austenite. Well, heavier cross section is something that can't be helped, but then if you have high cooling rate in the martensitic range and if you have fine grain size, then you have a better chance of reducing the residual stresses in hardening. Greater the tempering temperature, lower are the residual stresses. So, you are essentially reducing that stress. So, we have seen cryogenic treatment as a complete conversion, and this we have seen already. Now, there are issues in that can arise during heat treatment. You can overheat the material, due to which overheating can have a problem of reducing the kind of properties you are looking for. For example, if you anneal the material at a much greater temperature than what is necessary, then you will have a lot of grain coarsening. So, grain size coarsening, then you have softening of the material. So, annealing will soften it below the strength you want. So, basically the process is not in control, which means the properties also not in control. Burning is something that happens when there is oxidation at the grain boundaries. So, if you get oxidation at the grain boundaries, it means that the atmosphere in which it has been heated, the material has been heated, is bad, plus there could be overheating. So, there can be two things, one is overheating plus attack of oxygen, due to which you have rusting taking place at the grain boundaries, and then the material will disintegrate. Okay. Then you have oxidation because of again the problem with oxidizing atmosphere. Decarburization is also the outcome of presence of moisture and decarburization. In fact, very small quantities of moisture, for instance, even if you have 9 purity gas, meaning 99.999% pure gas, still it might have certain amount of moisture, which might lead to small amount of decarburization or at least a reaction at the surface, some reaction of the surface between moisture and the metal. Then there is excessive hardness of hot worked or annealed steel. So, these are number of issues like black fracture, that is free graphite, where there are graphite inclusions in the material, right, and as a result of that you have fracture taking place, basically strength being reduced because of the precipitation of graphite, and this is caused by excessive heating time and very slow cooling. So, now the graphite has plenty of time to diffuse out of the cementite or whatever phase it is in. Okay. And so, the remedy to that is heat the steel to a high temperature and forge it thoroughly. So, once you forge it thoroughly and then again get the carbon back into the lattice of austenite, and then cool it a little faster, okay, then it can you will not have this black fracture type of thing. So, there are many issues and the remedies are indicated here. So, there are preventive measures for each kind of issue, like corrosion, for example. You have pitting type of corrosion or groove type of corrosion. So, when you heat in the molten salt baths, as I said, you have chlorine ions particularly, which are very reactive and they can attack the grain boundaries, and so there can also be oxygen being present in the salt baths, right. And then the heating in flame furnaces can result in non-uniform scale formation. So, there are a number of issues while heating in the furnace. So, salt composition has to be controlled, or deoxidation of the bath has to take place, and basically oxidizing atmosphere has to be avoided at all times. So, there are a number of such possible issues with the hardening process, and so we will continue with this in the next class and see in detail what are the problems and how we can solve these problems. Thank you.